Ako na.
Good day to all listeners and to all presenters in this colloquium. I'm Benjo and my partner name is,
I'm fourth.
and we're here to present our research entitled The Use of Isothermal Titration Calorimetry to determine the thermodynamics of manganese ion adsorption from aqueous solution using nanozeolite. A brief introduction. Contamination on the Earth's water is always addressed a global problem. Heavy metals are known to occur naturally in the Earth's surface and can be sources of micronutrients that can help in growth. But these can be toxic and can be of great concern, especially if found in the food chain at the high concentrations. Since heavy metals pose a danger to both public and environmental health, eliminating dissolved heavy metals from water is a top priority for our society. Precipitation, ion exchange, reverse osmosis, membrane separation, and other traditional methods for extracting heavy metals from water have all been successfully tried. Uh, Isothermal titration calorimetry. Adsorption is one of the most promising and widely used methods due to its ease of use, high performance, and cost effectiveness. So, the technique that we will use is the isothermal titration calorimetry or the ITC. This equipment is the only technique that gives full thermodynamic profile of the binding reaction in one experiment, which is advantageous over an indirect approach, like the Van-Hoff analysis, which using calculations from theoretical equations are needed. Uh, are materials of interest. An element that can be found in nature is manganese, and it's usually found in our drinking water, especially at lower concentrations. It is important for human health. Excessive manganese concentrations, on the other hand, can cause water to taste metallic and cause a variety of health problems. Another materials is the nanozeolite. It's a three-dimensional microporous crystalline solids with defined structure, great absorbent due to their abundance of pores and cavities. Okay. Our objectives of the study. This research is focused on treatment for excess manganese in drinking water. This is also determine if nanozeolite is a viable adsorbent for manganese using isothermal titration calorimetry. The specific objectives are if the binding is spontaneous or non-spontaneous, how the thermodynamic parameters describe the adsorption process, to derive a phenomenological model that describes the adsorption mechanism for nanozeolite M2 plus or the manganese system, to identify if nanozeolite manganese solution is ideal or not. Here's a brief methodology. Um, Are all materials and experiments are located in Papua University, and our materials all came from the DOST. First, we prepare the manganese sulfate solution. Next, the preparation of the nanozeolite solution. We sonicate the two solutions and the gas, the water. Then we put it in the ITC to see the full review of the thermodynamics. Next.
Okay. For the results and discussions, we are tackling the binding thermograms, the thermodynamic parameters such as enthalpy, entropy, gives free energy, binding affinity, molar ratio, and the thermodynamics of mixing. So next. So in this graph is it's all the three binding thermograms for nanozeolite overlapping each other. The blue one is for the 20 degrees, the 20 degrees Celsius data. Red is for the 25 degrees, and green is for the 30 degrees data. So these peaks are associated with the incremental injections of the ligand, which is the heat released because of all our reaction are exothermic. And the baseline is established between each injection for accurate heat determination. So almost all throughout the series of injections, the peaks of the green line, which is the 30 degrees Celsius, are higher than the tree. So it is because the total energy absorbed in bond breaking is less than the total energy released in bond making between the adsorbate and the adsorbent. So it resulting in the release of extra energy in the form of heat. Therefore, change in enthalpy will be more negative. So here is you can see the thermodynamic signatures of nanozeolite and the thermodynamic parameters. We okay. And this shows all the parameters we've got from all our experiments, and we will discuss each one of them in details on the following slides. Okay, so for the change in enthalpy, the graph shows that as we increase the temperature, the value for the change in enthalpy becomes more negative. So a negative value for the delta H or the change in enthalpy indicates that all reactions are exothermic because the particles are releasing heat upon binding. Change in enthalpy tells us the quality of the bonds. To explain in detail, we will use visual representations. So the figure on the right shows the interactions of the manganese and nanozeolite at a molecular level. So at lower temperatures, it seems that the bonds of the adsorbate to the adsorbent is weaker compared to the bonds at elevated temperatures. So at 30 degrees, the bonds of the manganese with the nanozeolite are closer compared to the 20 degrees. Water molecules are smaller compared to the manganese particles. So when you increase the temperature, the Brownian motion of the water molecules also increases, causing them to collide with the manganese particles. And these manganese particles that are initially at the surface of the nanozeolite gets forced or pushed into the pores. So for the change in entropy, as temperature increases, the value for change in entropy decreases. So, change in entropy helps us tell the quantity of the adsorbed particles. So, in addition, a positive sign of the value of change in entropy indicates that increase in randomness of the solution. So, the figure at the left side, at 20 degrees, the Brownian motion of the water molecules is the main contributor for the initial entropy. Since the water molecules are smaller, more abundant, and lighter compared to the manganese and nanozeolite, so their movement is chaotic. So as you add the manganese into the solution, it will replace the adsorbed water molecules. So for this reason, many water molecules from the surface of the nanomaterials causing the system to be more disorganized. So, going back to the Brownian motion, an increase in temperature increases the Brownian motion of the water molecules, causing them to collide with the manganese particles. So instead of them getting adsorbed, they get pushed away. It can also dissociate the manganese particles, thereby absorbing more water molecules, which lowers the overall change in entropy, which becomes which becomes less positive at the solid solution interface. So increase in temperature can also prevent some of the manganese ions not to be adsorbed. So for the change in Gibbs free energy, all values of the change in Gibbs free energy for nanozeolite are negative, meaning its reaction is spontaneous and it implies that the binding is naturally occurring between the adsorbent and the adsorbate. This means that the reaction occurs without external energy input. So the spontaneity of the binding decreases as the temperature increases. On the other hand, if the value of changing Gibbs free energy is more negative, it is more favorable. So at 20 degrees, the value for the change in Gibbs free energy is more negative, meaning it is more favorable at absorbing manganese at that temperature. Okay. So for the binding and molar ratio, for the graph, the binding affinity is higher at 20 degrees and decreases with increase in temperature. So for the figure, for the Miller ratio, we can use the same visual representation used in representing change in entropy because they are directly related. So the molar ratio is the adsorbed particles, which is the manganese particles, over the adsorbent, which is the nanozeolite, and this is directly related to the change in entropy because it tells us how many manganese ions are adsorbed. So at 20 degrees, more manganese is adsorbed compared to the 30 degrees, implying it has a molar ratio and it supports by the more positive value of change in entropy. Okay, for thermodynamics of mixing, based on the results, the solution follows the non-ideal solution model for mixing the thermodynamics since change in enthalpy mix is not equal to zero. Furthermore, negative delta H or change in entropy indicates that the conditions are favorable and that the nanoparticles and adsorbate are mixing or interacting. So the release of manganese ion, which increases the entropic contribution of the said metal and lowers the total entropy, causes the mixture deviate further from ideality. It becomes more non-ideal as the temperature rises. So for the conclusion, the adsorption thermodynamic parameters revealed that the reactions of manganese to the nanozeolite are favorable, spontaneous, and entropic. The effect of change in temperature in the binding of the nanomaterial is that as the temperature increases, the amount of the enthalpy contribution also increases, thus decreasing the entropy contribution. Lastly, our type of solution can be classified as non-ideal. So for the recommendation of for further study, we found that the binding of manganese to the nanozeolite is favorable, and the binding is not as effective as we expected. Even though a nanomaterial has more surface area because it is nano-sized, which is a good candidate for absorbent. Our binding affinity is low compared to others found in related literatures. It could be that our concentration at pH values is controlled, so that is why we have come up with limited results. So maybe modifying the pH and concentration values could be used for further improvements of the binding interaction of these two components. In comparison, absorption, isotherms, and kinetics, the thermodynamic study of absorption data lacks a theoretical foundation. In this regard, the identification and explanation of the underlying thermodynamics in various absorption systems is the next real challenge to the absorption sector. So it is suggested that more research into developing in this field be done. So that's it. Thanks for listening.